We get our electricity supplied from power stations that distribute alternating current. But many of our devices, perhaps the ones that we love the most, such as our phones and our computers, require direct current in order to operate. So, what we need is a way of converting this alternating current into direct current. And the way we do that is through a process called rectification. To rectify something means to make it upright. So what we're doing is we're taking a sine wave that looks a bit like this, and rather than have it become positive and negative, we want to make it upright, like this. Now there are a few different ways of doing it. A simple way to have something that is upright is to simply remove all the things that are not upright. To remove all the negatives in this example. So here is a rectified AC signal. It's been rectified, so it is now only positive. It is direct current. So notice that direct does not mean that it is constant and positive. Direct means that it does not have any negative values. Pause the video for a moment and see if you can draw a simple circuit that will achieve this effect. You might think you know how to do it, and to be honest, you quite possibly do, but take the time to sketch the actual circuit diagram properly so you are ready for the next question in a moment or two. So the simple circuit is to have a single diode in series with whatever we are measuring. So for my circuit, I've decided to draw an AC power supply and a diode in series, with an ammeter to show this is where we are checking the current direction. Here is another example of a rectified signal. For this one, we've not only stopped all the negatives, but we've actually flipped them so they are now positives. This type of rectification is called full wave rectification because now all of the sine wave has been rectified. This has an obvious advantage that now there is always electricity flowing. Well, okay, maybe not at this very short moment in time, but pretty much all the time there is some electricity flowing. Now, this one is tougher. Can you pause the video again and try to draw a circuit that will achieve this effect? I'll give you a clue in a moment. Okay, if you are struggling, the key to this one is that all you need is a power supply and 4 diodes. The tricky part is knowing how to connect the 4 diodes together. Have another go. Alright, so make sure you did pause. I'm now going to give you my final hint, which is the bare bones of the circuit diagram. I'm going to put my ammeter in over here and my alternating power supply here with these connections. What diodes go in each space? Alright, so here they go. Notice that all the diodes are pointing towards the right, and that actually makes it easy to remember. You still need to get that wiring connected, obviously. But how does it work? Let's consider current flowing this way out of the power supply. It goes around here and reaches this junction. The left diode is blocking the current, so it goes to the right. Again, at this junction, the current can only flow this way, so it's going down through the ammeter. The circuit is not finished yet though, so at this junction it could go up or down, but remember that the current is also being pulled towards the other terminal, so it takes the easier route, like so. And it's back. When current flows the other way, we can trace the path like this. And we see that the current goes down through here again. So the ammeter always measures a positive current. The problem is the amount of electricity is always changing. We have a direct current, but the value of that current is fluctuating all the time, and for some short moment in time the current is zero. If we want even better than this, we need the next step of rectification, which is called smoothed full wave rectification. Taking this current circuit, how could we provide a smooth signal, and can you explain it? Hit pause one more time. Alright, your hint this time is that I want you to add a capacitor. So where does it go and why? Well, all we need is to put a capacitor here in parallel. At first, the capacitor charges, but when the power supply drops in potential and becomes lower than the PD across the capacitor starts to discharge. And this provides a boost to the overall PD and therefore helps the current stay stable. And that's the full description of rectification. You should be able to sketch the graphs and explain how each method works, paying particular attention to the shape of the smooth full wave rectification. We're going to assume that it still goes to the peak and that it drops linearly until it reaches the next cycle on the wave. Try building the circuit because, like all electronics, it tends to make a lot more sense when you actually see it working.